we're kind of in a little bit of the wild west of battery technology right now.
The challenges that are coming up for battery storage systems, the top 3, 4, 5.
Oh, narrow it down to 3, 4, or 5. I'm ranting a little bit.
You gotta rant, Mike, you gotta rant. That's why we brought you on.
We're about 5 years after some of those first initial builds were put into the ground. So I think that 2024 is gonna have a big recycling challenge and a big augmentation challenge as well.
Well, this is all way over my head, so let's move on. All right, welcome to another Sounds of Solar podcast. I'm your host, Christoph Brun, and joining me today is my esteemed co-host. Who are they?
Prahlad Shivshankran.
Russell Hamilton.
Wonderful. Gentlemen, we have a lot to cover today in the world of battery storage. But first, I still want to talk about Pradeep's sweater. Very nice sweater.
Thank you.
Looking very wintry.
It's, again, styled by Costco.
Yeah.
So I love Costco. So
Were you paid to say that?
But I wish I was, but no. Sometimes I just go to Costco just for the fun of it
Right.
and not get anything. It's kind of weird. You just run through all these aisles. You've seen everything, but you end up not buying anything.
How big was the last TV you bought from them?
To be honest, it's funny you asked that. 75
75 inches. Look at this guy. You can watch it from a mile away. Russ, how are you doing?
I'm doing good. Yeah, life's good.
Anything notable?
Not really, to be honest with
What?
you. I couldn't think of anything.
What'd you do in the last 3 weeks, 4 weeks since we last recorded?
I enjoyed the warm weather.
Oh, yeah. Well, yeah, we had a record warm December rain on Christmas Day. I mean, what is that?
For 1 year, I like it.
I'll take it too.
I think if it happened 2 years in a row, I'd be a little upset.
Yeah.
And Russ won the ugly sweater contest. I love that.
I did win the ugly sweater contest.
It was the ugliest thing I've ever seen.
It was very terrible.
We should put it up there.
We'll put a link. I'll send you a picture. We'll put a link up of it. It was scary.
If you see that, it will take some years off of your life.
But I knew it was a guaranteed winner when I bought it. So.
Well, I'm sorry that the listeners and viewers of the show have to see this, but it is what it is. But anyway, moving on. We've got a very great guest for you all today, Mike McKinney, battery storage expert at EBS here. Mike, why don't you tell us about yourself? Who are you? What do you like to do?
Yeah, thanks for having me on. I'm excited to be here. I'm Mike McKinney. I guess I'm like a lead technical engineer on the design side, focusing a lot on battery energy storage systems. Outside of that, I guess my background is a little bit of a jack of all trades scenario, mechanical engineer for a few years, civil engineering, asset management. I've always had a passion for renewable energy, though. Actually, when I was about 19, I did fabrication, welding, sheet metal for a little small mom and pop solar thermal outfit. So
nice.
That kind of got me interested in renewable energy and came up here to the great state of Minnesota, joined up EBS, and here I am.
Where were you from originally?
From Jacksonville, Florida, actually. So.
Oh, okay. Are you
Big
still
change.
a Jaguars fan? Or?
Yeah, I hear they're doing good. Aren't
Okay,
they?
yeah, I don't know.
I'm
I don't
not
follow
much-
the NFL.
I don't really follow
That's the first thing
sports,
that
but-
came to mind for
Yeah.
Jacksonville.
Sports
There's
ball.
also Leonard Skinner. There's Limp Bizkit.
Oh, I didn't know. I'm a
as
huge
music
Skinner.
guy,
I'm a
yeah.
huge Skinner. I
Yeah,
thought they were
yeah.
from Gainesville.
No, Jacksonville. I grew up. I
Tom
used to
Petty's from
play at
Gainesville, isn't he?
Ronnie Van Zant Park, named after
I am such a huge Skinner fan.
Yeah.
I feel horrible for not knowing that. I better
Yeah.
quit the show. Well, now I forgot what I was going to ask you based on that because I feel so upset about my life. But
But I
Well,
think
speaking of music, I think we share some hobbies. We're both musicians, both like the mountain bike. I
Mountain
think
biking.
you take it a little more seriously than I do.
I'm hopelessly addicted to it, so
Yeah.
it's unhealthy at this point.
What instruments do you play?
Drums. Yeah. I've
Do you
been
sing
playing.
too?
No. Maybe if I'm drunk enough.
Got it. Love
Not-
it.
Not like this guy.
Yeah.
We might be looking for a drummer, just FYI.
Oh, yeah, really?
I don't know
Well,
if you're in the market, but
Yeah.
Making connections.
See me after class.
we'll take we'll take that offline. Mike, can you give us a high level 35, 50 million foot view of what BESS is?
Yeah. So when you dive into it, when we talk about batteries in general, you've got primary and secondary, I think is a good way to start. So a primary battery is like your AA battery or a watch battery, generally something with like an alkaline chemistry that's going to degrade over time and it's kind of one and done use. Moving into battery energy storage systems at a utility scale, it actually works on the same technology as like your smartphone battery or your laptop battery, even electric vehicles. It's all lithium ion, what we call secondary batteries, where you have lithium ions that can move back and forth between the anode and the cathode through an electrolyte and a separator. And this way, it's a repeatable process. So it can go back and forth, and it's pretty exciting stuff. Prahlad's worked on several projects with me in this regard, and generally speaking, they're large containers, with the lithium ion battery technology, as well as auxiliary power systems, HVAC controls. I mean, they get very, very technical very quickly.
Well, I mean, what would you say? Lithium, I think, is a charged term. That's a horrible pun. I'm sorry. What are we at the end of lithium? How is it going to be continuing? The thermal runaway problems. Like, I think there's a lot of issues with lithium that new chemistries are emerging that pose better options in the future. Is that accurate?
Yeah, it's tough to say. I think that we're going to be generally on the concept of lithium ion for a while. I think that there's going to be a lot of technological improvements on the internal components. Like, for example, people are experimenting with sulfur, with peroxide, that kind of stuff for the cathodes themselves or the anodes. And graphite's another technology. But what's interesting to me when it comes to batteries is I do think it's one of the final frontiers of science is chemistry and material science. Stuff like thermodynamics and electromagnetism. Like, we've got that kind of stuff figured out. Aerodynamics. There's a little pieces of efficiency here and there, but to your point, I mean, battery technology could be radically different in the next few years. It's hard to say. As far as the general concept of lithium ion, though, I like to think of lithium ion in a little bit of a similar way as like silicon is to photovoltaics. I mean, it's just at the moment, that is the best ion that can move through the separator, through the electrolyte. People are experimenting with sodium as a possible replacement, but I think that there's a lot of gains to be had with the lithium ion technology, just experimenting with different materials for the cathodes and anodes. Like lithium iron phosphate, for example, is a big one there that we've worked with a lot.
And that helps. The LFP technology was mainly...
What is LFP?
Lithium iron phosphate. So by including certain components and changing the chemistry, they were able to get the thermal runaway problem kind of resolved, in the sense it now requires a lot more of a temperature. It needs to reach a certain temperature to fail. So now because you gain that extra time, you have protection schemes that you can include to kind of safeguard the battery. I think that's so things like that, like what Mike was saying, is innovations. So lithium itself, I think, just listening to, again, Elon Musk, and how I love Elon Musk, the actual lithium itself seems to be not the problem. It's different components of lithium that are actually the problem in terms of supply chain. So yeah, just innovating and trying to gain efficiencies with what's already, like a technology that's already proven, is sort of what people are doing right now.
Right.
And then the next step is to get that supply chain flexibility with different, like something like a sodium. And sodium also addresses the thermal runaway issue. There's some companies like Neutron Energy that supposedly you can fire a bullet at the battery and it's okay. So.
Jeez.
I mean, that's a great marketing ploy, I guess. But
well, we do have a lot of projects in Texas. So.
Yeah.
Are you insinuating that people shoot batteries in Texas? People shoot batteries here too. All right. So you're bringing up the sodium thing. I know I can't think of off the top of my head. Who is it? Maybe Ambry is the liquid metal battery. Is that a sodium based battery?
I could be.
I know CATL has been experimenting with some sodium ion builds these days.
I mean, part of that is that the availability of lithium versus sodium. I mean, sodium is hyper available, right?
Yes.
And like, there's something to be said there too about material resources and availability.
Right.
That lithium, and that's maybe where I was coming at also with it. The mining aspect of lithium is complicated at best.
Yeah, a lot of water injection from how I understand it into the systems. And, I agree with you. I think lithium is going to be the next, scarce resource that everybody's after. And you have to think also as well, the variety of different applications that utilize lithium, right?
Yeah.
Again, smartphones, electrical vehicles, laptops, now large BESS systems that, if you look at projections over the next 5-10 years, I mean, it's just growing and growing and growing. I mean, the capacities are getting insane.
I think that's kind of a good segue into the challenges that are coming up for battery storage systems. And what are you seeing that is probably the top 3, 4, 5 issues that we're facing going into 2024?
Oh, narrow it down to 3, 4, or 5. I think that form factor is a big one. And I think that companies are starting to get a handle on this. But I guess what I mean by that is a little bit of a standardization into the field. We're kind of in a little bit of the wild west of battery technology right now, as far as people, a lot of companies, a lot of EPCs, a lot of developers, these are their first large utility scale systems that are coming online in the past few years. So understanding how the production fits into Lego pieces, if you will. Solar is a good example of that. Solar, the form factor is kind of standardized right now. Generally, solar panels are about 2.2 meters by like 1.1 meter, right? So it doesn't matter who you get that from. You can expect that standardization, for the single axis trackers or the fixed tilt or what have you. So I think the challenge on the construction side right now for batteries is standardizing to a form factor. We've seen what containers are starting to standardize about 20 to 30 foot.
I would say 20 feet. And what he's talking about is like we have people or companies doing a modular approach, maybe like a Fluence cube versus a single container, right? So and now Fluence is thinking about a single container, which is a product that they're coming out with. So maybe there are different use cases for these different products. Like a DG project may not need a big 20-foot container, right? It could just go ahead with something more modular and add on augmentation later.
Sure.
But containers generally seem to be standardized around 20 feet, and now they are trying to push more. So the energy density is starting to go up within that same footprint.
Are you seeing a difference in between these modules, if they're AC coupled BESS or DC coupled BESS?
I haven't personally. I think the major difference with those two systems is the need for a DC-DC converter, which is another separate system. And to your point, I'd be curious to see in the future if people can, or integrators can sort of put that technology within the containers. Because I think what's very challenging from project to project is, maybe on this one project with, this certain manufacturer, it's an all-in-one container. And then another manufacturer, now you've got the container, and then you've got the disconnect switch that's separate, and you've got the water system that's separate, and then you have the auxiliary panel that's separate. So that added complexity on the DC side is on that converter system, which I would like to see built into containers moving forward. And I think that, to Prahlad's point, standardizing to 20 to 25 feet containers, but also I'd just like to see a lot more consistency. I think another big challenge on battery sites at the moment is auxiliary power and getting that. It can be kind of a Rubik's cube of transformers and switchboards to kind of distribute this all. And this system wants 208 single phase. This system wants 480. So I would really like to see moving forward in the industry a little bit more standardization on auxiliary power, right? Like, my inverter needs 120 single phase, but my battery container needs 480, but I'm only getting 34,000 volts from the substation, so this gets really complicated and gets really expensive very quickly.
What does auxiliary power mean? I mean, you kind of just explained it, but maybe just dumb it down for...
Sure. So auxiliary power is essentially... The thing about lithium-ion batteries, we talked about a lot of the positives, right? That they're secondary batteries that you can charge and discharge them multiple times, but they're incredibly fragile technology. They're very temperature dependent, and it's kind of insane. Like from the moment they leave the factory on the ship, most of this is produced in Southeast Asia, Korea, China. And the moment that they're on the shipping transports, going to California, and then on the semi-trucks, going out to the sites, I mean, they have geotag monitoring everywhere. They're monitoring temperature, they're monitoring humidity. And the second any of that goes out of bounds, you're voiding the warranty.
Exactly.
And we're talking about millions of dollars of loss. I heard the other day when I was on a site, I heard a story about an entire shipment of battery racks that got voided because the semi-truck jostled a little bit in the back. In one of the outside containers, like, the wrapped up cardboard, that got pierced a little bit. They said that's it for the whole shipment, so it's very careful because of what we talked about earlier, which is thermal runaway. Maybe I'm ranting a little bit. We can
You
come
got to
back to that
rant,
one.
Mike. You got to rant. That's why we brought you on.
Let it out.
But to answer your first question of auxiliary power, it's mostly for HVAC. So I was talking about all the temperature control because the majority.
And for those who don't know HVAC, I mean, everybody
Yes.
should know it. But
air conditioning systems,
Yeah.
heating, ventilation, and air conditioning, HVAC. Yes. So the biggest loads on the auxiliary side are giant HVAC containers. We've seen liquid cooling really trump the market nowadays. It used to be air cooled that we would see a lot. Like those barred like outside containers. Like if you've ever seen like Connexes on a construction site with temperature dependent stuff, they'll put those out there. So that's kind of where it started. But now it's got to the point where it's all like liquid cooler, like computer processors and like gaming PCs.
Yep.
It's very similar technology with like fluid cooling plates and that sort of stuff. So your largest load is definitely going to be those HVAC loads, but there's also an incredible amount of control that goes into these,
Controls,
which is
light,
dispatching and BMS, and that's a whole nother rabbit hole to go down there. So,
But auxiliary power is just like coming back to that is like running everything that isn't the actual power generating facility, right?
yeah,
Okay.
a good way to think about it is auxiliary power is all the other stuff that has to go on to get your goal. Which
And there's
is
so
the
many
charge
things to match,
discharge.
inputs and outputs
Yep.
to match during that whole thing.
Exactly.
can you touch on benefits and pros and cons of AC coupled BESS and DC coupled BESS? I wanted to go back to that.
Yeah, absolutely. So DC coupled BESS is how you think about it in your head. I would say that.
What does that mean?
So, well, hear me out. Maybe I'm crazy. But when you think about a solar and a battery system, what do you think of? How do you think that works?
When you think about a solar panel and a battery, well, the sun, which is so powerful, charges a panel and something happens in it, and then it pumps that stuff right into the battery.
That's a DC coupled system.
Boom.
See, am I not crazy?
Is it the
now?
same way? It's think about it the same way as like your battery charger, right?
Sure. Yeah.
Your phone
pretty much.
charger.
Right, sure.
It's an adapter. pretty
So
much.
it's essentially, with the DC coupled system, you're utilizing the excess solar. So there's this concept in solar design called clipping or DC-AC ratio. So inverter outputs only have so much that they're going to inject to the grid, right? So much MVA. So that excess can go to charging batteries in a DC coupled system. Excess of what the inverter has kind of promised or been programmed to send to the substation.
I
So
see.
instead of that
Yep.
energy going to waste, it goes to charge the battery banks.
Okay.
And then when the plant needs additional production, when it's a cloudy day or it's nighttime or whatever, the DC batteries can then go through the DC-DC converter to the inverter and then dispatch to the substation.
Do we have an idea of so I'm going to try to be technical here, non-DC coupled BESS solar generating facilities, how much waste? Is there waste energy?
So you're talking about AC coupled BESS.
No, I think he's talking about like clipping.
Clipping.
Yeah, like if you're saying like, okay, if there's excess energy, it goes into the BESS.
Yep.
And if that is not there, does any of that energy that is pumped into the grid then, is that wasted, quote unquote, or not necessarily?
We can model that with production modeling software. So that'll get typically PVSys is a big one on the market that can kind of give you some loss diagrams of basically just lost energy. But most of the time that's actually based on POI requirements. So at the substation,
point of inverter.
Point
of
of
Interconnection. I knew that. That was a test.
At the substation, they might have a cap on how much that they can inject to the grid, and I think Prahlad talked about this on a previous episode because you can't overload, right?
Yep.
So if we have a solar site and we say we're 100 megawatts AC, we can't really inject 175, 180 because what if the infrastructure is not prepared to handle that? So a lot of that clipping can actually happen at the substation level as well, and then it can also happen on a cool sunny day. I know it's counterintuitive, but solar panels don't like to get hot. They like to have irradiance. It's a little bit of a different thing. So on a cool sunny day, your solar panels will be producing at maximum power. So there, the inverter could potentially clip as well. So I think those are your two main areas of clipping, either at the inverter side or at the POI if we're just really pumping a lot of generation and it's just more than we've told the grid we're going to give them.
The exact parameter you're kind of talking about is just the DC-AC ratio. And I guess generally we see 1.3, 1.4 DC-AC ratios. One aspect is like with that, you have some clipping. That extra 30% is just clipped energy. two factors there is one is the POI thing that Mike just talked. The second is the degradation. This thing needs to last 25 years, right?
Yeah.
So that extra 30% needs to account for degradation.
Right.
And yeah, that's I think one of the biggest reasons. as
Also,
well as
keep in mind
climate
too
change.
that the overbuild is because standard test conditions, right?
Yeah,
Which
correct.
is 1,000 watts per meter squared,
Right.
air mass of 1.5, I think. So when we're not at those perfect conditions, we're
Yeah.
not going to be producing as much as we think we are on paper,
Yeah.
right? So 550 watt solar panels only going to be producing 550 watts at standard
STC,
test
yeah.
condition, right? So that's a little bit why we overbuild as well. But AC powered, to answer the second part of your question there, or AC coupled solutions actually are a little bit separate from the panels. I know we have big projects and we say, here's the solar panels, here's the battery yard, they're both connected to the substation. And you'd think, again, intuitively, well, the solar panels charge the batteries, right? That only happens on the DC system. On an AC system, they both contribute to the grid, but it's not necessarily the solar panels that are charging and discharging the batteries. So the batteries are playing a game in AC systems that we call energy arbitrage. And essentially what they're trying to do is they're trying to charge up when the demand on the grid is low, and then they're going to discharge when the demand on the grid is high. And it's not out of the goodness of their heart. The
Not always.
the cost of energy changes based on those two. So they're kind of playing a very complicated game of a electricity stock market. They're buying low and they're selling high, and that's how the systems maintain profitability.
That's like the same principle behind pumped hydro, right? You pump
Yeah.
pump it at night when it's cheap, you discharge it during the day when it's
Exactly.
expensive, blah, blah, blah.
One of the big difference too, I just wanted to touch on so folks that maybe don't know, a DC coupled BESS is going to be a battery system that is installed at the inverter. An AC coupled BESS is going to be in a completely separate yard.
Exactly.
And that's like another difference between the two is land usage, right?
Yeah. So I have a question for you, Russell.
Sure.
Flipping the table on you.
Yeah.
There we go.
AC coupled systems, generally speaking, we locate these battery yards right next to the substation. What kind of challenges from the study side have you seen with that? Or do you think that's generally a good trend moving forward?
From a studies perspective, DC coupled BESS is a much more complicated and difficult system to figure out. The AC coupled, since it is actually separate from everything, we treat it almost like a substation.
Yeah.
In the way that we look at our studies, and that they're actually not that complicated or difficult. So I would say the AC coupled BESS being separate and then close to the substations, it's easy, it's fine. I think it's a good design. So the DC coupled BESS is very, very, very challenging.
Which studies?
Just probably from a
specifically?
grounding perspective?
Yeah.
No, it's from ampacity is a huge one because
sure.
now you have all these small area and you have all these cables running
Yep.
underground. Losses are difficult to figure out. Nighttime VAR is a little bit more difficult to figure out. But grounding isn't really more difficult, I wouldn't say. It's actually probably less difficult because now you're just within the confines of the PV yard itself.
The only thing with the grounding I still haven't figured that out, but when we did DC coupling, when I was with Alan Cohn, we did something galvanically isolated converters so that the grounds are separated, like you don't have interactions. But in what we see on site, on average, you see like regular converters where it's not galvanically isolated. So you have the grounds shared. So that's something I've never really understood. I don't know if you guys modeled that or that's
Yeah, we modeled the grid as a complete system.
Okay.
So it's the entire site is electrically connected. Grounded. bonded.
grounded. Okay.
Yeah. And that helps with grounding because you want a low impedance system for grounding to be really effective.
Okay.
And so the more copper or metal, it doesn't even have to be copper, aluminum, metal, steel in the ground, the lower your impedance of your system is going to be.
Interesting.
Well, this is all way over my head, so let's move on. No, Mike, also, what about like the regulatory code compliance, some of these other considerations, challenges in BESS moving forward? Also construction, like what about this other aspect of BESS?
Do you have 4 hours?
No, we've got about 4 minutes.
So on construction side, or on code compliance side, we could start there. I want to see faster adaptation from states on NEC regulation, or at least some sort of buy-off from clients and owners saying, you know what, even though the state adaptation is only on 2008 or 2020, we're going to go with 2023 because 2023 actually put a lot of really good stuff into the code about battery energy. Again, battery systems are very new technology. We're all kind of figuring it out together, but the new regulations that came in 2023 really clarify a lot of like technical spots where beforehand Prahlad and I and some other technical engineers here were, a lot of it was up to our interpretation or engineers of record, but now they stated a lot of things a little bit better. So additionally, I think the challenge with compliance and regulation is making sure, and it seems common sense, but making sure that these manufacturers that are in Southeast Asia are building their systems to North American regulations. Making sure we have all the right UL listings, all the right IEEE standards are being followed. We're following the NEC or the NFPA 70, coordinating with the AHJs to make sure that they are comfortable with the systems, because we touched on it very briefly, but thermal runaway and also very, very large fault currents from lithium-ion batteries are very dangerous. I mean, it's a new technology. It's cool, but it's also very it can be catastrophic if done incorrectly.
The energy is equivalent to like lightning strike or something?
100. You're talking if one battery container faults, you're talking 100 kiloamps of current can get pumped through at 1500 volts.
That sounds like a lot.
It's quite a bit. It's like the cartoon where you get blown up and just your smoking boots are left. And then on the second question with constructability, I hope moving forward we're going to see improvements in energy density. I personally think that energy density is a little bit more important than power density for utility scale applications. And the difference is how long it can charge versus how much it can release at once. So seeing more energy density, in my opinion, is going to be great, because just on any site that we work on now with like regular solar, sites are getting harder and harder to come by. Land's getting more challenging. We have to build in very innovative spots. So we're oftentimes stuck with the puzzle of trying to fit 2 gallons in a 1 gallon container. And then, as Russell talked about briefly, ampacity, or just making sure we have enough room for all these high voltage, high amperage underground conductors without too much cost to the construction. This is something I really hark on whenever a new battery project's on my plate is, right from the get-go, let's make sure that not only are we spacing equipment, for clearance requirements, but we're also considering, how large our trenches are going to have to be for these, for construction. So I'm hoping to see more power density, more energy density in the future. Have you ever seen a site, Prahlad, where they actually stack them? I've heard of these things a bunch of times, but
I've heard that,
I'd like to see that a little bit more. I think that's your problem more than ours, though, from the structural side, making sure.
We can do it.
Yeah.
We'll make it work.
And
making sure
HVAC
wind loads and all that kind of stuff. But stack these containers up. I mean, do what you got to do. But make sure we have room for our conductors.
Interesting point that Mike made it just hit me, was like the clearances. A lot of the times when we open up a manual or a technical document, we get clearances from the battery manufacturers. That clearance generally is a clearance that's sort of approved by UL, because they need to test it. There's a 9548 testing, which tests the system and makes it fail intentionally, and the spacings are kind of dictated by that. The one thing I would like to see is if they can consider cables running on, like just cables running to the PCS while they do the testing. It's a way by which we could standardize it, because the battery manufacturer would say, okay, have a clearance of 8 feet. Then it comes to us engineers, we're like, dude, these guys are crazy. Like 8 feet, like we can't fit anything in this. And then we just space it out. So that you can reduce that complexity by being like, hey, we already figured this out. This should be enough to.
It would be nice, but they throw that on us.
Yeah, they throw that on us.
Consulting engineers, and it's a very difficult. To Prahlad's point, that's a difficult thing to sell our clients who are, very land restricted, and they're trying to fit as much capacity as possible. And they say, well, hey, we looked at the manual. It says you only need 8 feet. And we're like, no. Depending on the conductors you're buying or the thermal properties of the soil, you're going to need a lot more than that.
Yeah.
So that's a hard message to give the client.
I'll say that's a big one right there. Is it's hard to standardize something like that because every site is different.
Yeah.
Or using concrete slurry.
Exactly.
Or using copper or aluminum.
Yeah. We even looked at one project that was DC coupled BESS. We spent a lot of time looking at like underground Trenois trenching.
Sure.
Cable tray.
Yeah.
Yeah. And they didn't end up going that route, but we had so many cables in a small corridor that would have really helped out, but it was very expensive as well.
That was above ground too, right? So
it was above ground.
Yeah. Mm-hmm. So that actually gives you a lot of thermal advantages if you can figure it out. But cost implications are probably the big hurdle there.
Yeah.
So moving on to the final part here, looking forward into the future, research trends, market trends, predictions. What are you thinking? What are you looking for as BESS moves into 2024 and beyond?
Can I add to
go.
that too?
Yeah.
Do you think, as well as that, do you think that existing solar sites are also going to get retrofitted with BESS?
Good call. Good question.
If there's available land, then yes, I think so, because you've already built the substation infrastructure there, which I think is one of the hardest parts of getting new sites, generally speaking, for renewable energy, whether it be wind, batteries, or solar, is all the transmission infrastructure, right? So when you've already got the substation in place, you've got the high voltage transmission lines, let's get as much as we can out of it. Moving into the future, I think that lithium ion is probably here to stay as far as just the standard technology of how we're moving from the cathode and anode with a positive, a lithium ion positively charged, looking for that electron. I think that core like physics science is not really going to change very much. Maybe we'll see sodium replace lithium, maybe. And then also there's a lot of room for improvement in the technology itself when it comes to new advancements in material science and chemistry to replace with a better anode, a better cathode, a better separator, those sorts of things. Solid state is also, I would like to see solid state get rolled out. I think one of the...
What does solid state mean in this context?
Yeah, so generally with a lithium ion battery as it is, you have your anode and your cathode, right? And then the electrolyte is a liquid. And the lithium is moving back and forth. And this can cause thermal runaway because the separator in the middle, if that starts to break down or if it gets too hot, it can kind of chain reaction and then, catch on fire and start catching on fire its neighbors and that kind of stuff. The solid state version of this works on the same principle, but instead of a liquid electrolyte, it's a solid electrolyte. And those are going to be much safer. I think that when we move forward, we might see solid state batteries and they might have a better energy and power density, which I think are the big trends in the industry right now, or the big things to look out for, is who's making, we're kind of in an arms race of battery technology, right? Like who's making the batteries with the best power and energy density to meet these very strict land usage requirements. Right. So I think that that's what I'm the most excited for is, again, I think that the sky's the limit in those two fields, in chemistry and material science, and batteries are just going to benefit from that the most. Now, another challenge I think is getting capacity from manufacturers. I think a lot of the big players in the industry are buying up as many batteries as they can and storing them. So it's a big production issue right now, I think. We need more batteries faster, because if you look at any kind of charts online, I mean, just at home, if you're at home, Google, battery installation projections 2030, 2040. I mean, it's just up and up, and it's going to be everywhere. So,
and one thing that I wanted to add there was just standardization of augmentation strategies. I think having like a string level approach where string inverters in a battery skid allows flexibility and technology changes. I'm hoping that happens, because a lot of times when we get to these projects, nobody talks about augmentation. They're like, we'll deal with it when it happens.
That's a really good point, actually. I think one of the big challenges in 2024 is augmentation, because a lot of the initial builds are getting to that point where now it's 4 or 5 years old, and now they have to think about augmentation. And if you didn't plan for that originally, now you're kind of scrambling. And then also, how do we recycle?
I was just going to bring that up. Like, what does it look like to recycle? What is the life cycle or lifetime of these BESS, battery storage systems?
The realistic one and the actual one.
Right, yeah.
Because it's probably, 10 years?
10 years.
But it's
you might
really
get 5.
You're right on the money.
Yeah.
So
10 and 5?
10 and 5 is about right, yeah. And I think that we're about 5 years after some of those first initial builds were put into the ground. So I think that 2024 is going to have a big recycling challenge and a big augmentation challenge as well.
So that's like going to be a whole new industry created, though, right?
Yeah,
Recycling of these batteries.
The same with modules is,
module
any repower, oh my God, millions of modules that need to be recycled, and someone's got to figure that out.
I did want to ask if there was an efficiency difference between using lithium ion and solid state.
I'm actually not sure just yet. Solid state's not out yet. It's going to be an upcoming technology.
Okay.
But I would imagine if you look at solid state technology generally, I'm thinking like solid state hard drives
Hard
first,
drives,
you know, physical hard drives. You know, I think that that's going to be, again, the big buzzword of power and energy density. So I think that even if efficiency might be a little bit lower, the fact that we can put so many more into the same space
Sure, yeah.
would make it.
But I think just like to Mike's point, that solid state avoids this dendrite kind of sharp things happening in the electrolyte and poking through. But I think it'll happen. You'll see solid state being used by the car industry first, before it even comes to energy storage.
Yeah, to utility scale.
Yeah, I think it's going to be
a good point,
while.
because weight is
Yeah.
much more important for EVs.
Yep.
For us, I mean, as long as we can ship it and put it on a truck, it doesn't matter how much it weighs. And it's very surprising sometimes. You'll look at spec sheets and be like, wow, that one rack weighs like a ton. Like, it's insane how heavy these things are.
Well, I think that concludes it, gentlemen. Mike, thanks so much for joining us today. We learned a lot. Most of it was over my head, but it seems like you guys understood some of it. For the viewers and listeners, please, the best thing you can do, leave us a review, share with your friends. You know where to find us. It's not that hard, right? But the reviews and sharing definitely helps. I think we'll see you next time on the Sounds of Solar podcast, and take care.